Right now, millions of tons of invisible gas are being forced under high pressure miles below the surface, locked permanently into deep rock formations. If we entirely stopped burning fossil fuels tomorrow, the residual heat and existing atmospheric carbon would still push us past our 2030 climate targets. Because conservation alone cannot mathematically close that gap, engineers are actively building machines designed to pull carbon dioxide right out of the sky and straight from industrial exhaust flues. Executing this requires an entirely new, massive industrial infrastructure. By 2025, the scale of carbon capture and storage networks will begin rivaling the physical footprint of the existing oil and gas industry. We are essentially running the industrial revolution in reverse, building a global infrastructure of wells and pipelines designed to handle billions of tons of gas. The exact journey of a captured carbon molecule usually begins right at the source, inside towering metallic columns attached directly to refineries and power plants. Looking at this 8RH2 schematic, heavy lifting industrial physics traps the gas. A convective reformer strips out pure hydrogen, capturing over 99.5% of the CO2. Instead of expensive solvents, it recycles tail gas thermal energy back into the combustor for maximum efficiency. Heavy industrial physics covers the large-scale exhaust, but biologists are turning to nature's microscopic capture technology, specialized proteins known as carbonic anhydrases. Companies like Novonesis harness these biological agents. In a water environment, a single enzyme molecule can force 1 million carbon-trapping catalytic reactions every single second. Scientists are now taking these hyper-fast microscopic enzymes and scaling them up by the ton to line the insides of massive factory exhaust systems. Extracting enough carbon to cool the planet requires deploying both of these extremes simultaneously, the brute force of massive thermal loops and the accelerated precision of engineered biology. Trapping the gas at the factory is only the first hurdle. If it stays at the smokestack, the cleanup stalls out completely. Before the raw carbon can be moved safely, it passes through dedicated gas dehydration and conditioning units, systems like Capsolgo, that strip out impurities and highly compress the gas for transit. Once conditioned, the high-pressure gas is injected directly into a vast continent-spanning network of heavy overland steel pipelines. To keep tracking how we are physically engineering our way out of the climate crisis, hit the subscribe button. Without this exact logistical middle step connecting capture sites to storage zones, the carbon remains trapped in the factory flues, leaving the entire sequestration cycle stranded at the source. At the end of the pipeline, the carbon arrives at its final destination, geologic formations deep underground, completely removed from the atmosphere. Energy groups like Secoftis bypass active reservoirs entirely and instead pump the compressed CO2 directly into extremely deep, unminable coal seams. This cross-section demonstrates a physical mechanism known as adsorption. When injected into porous coal, the CO2 molecules physically lock into the rock's microscopic crevices, permanently displacing the weaker gases that were already there. The immediate concern for any community living above these injection sites is containment, specifically whether this highly pressurized gas will eventually migrate back up to the surface. To monitor that exact risk, engineers use active spot seismic arrays. By bouncing high-frequency sound waves off the deep rock layers up to 40 times a campaign, they maintain a real-time tracking alarm on the exact shape and movement of the underground CO2 plume. The end of the value chain is a highly instrumented, permanently monitored geologic vault designed to keep the gas trapped for millennia. While billions are poured into these heavy subterranean engineering projects, a parallel storage effort operates right on the surface. Recent studies, like the 2024 Napa Green Report on vineyards, demonstrate how specific regenerative agricultural practices force carbon out of the air and permanently bind it into the active soil microbiome. When you map it all out, the biological soil sinks, the hyperfast enzymes, the massive thermal refineries, and the deep seismic coal vaults all belong to the exact same global ecosystem. Because conservation alone cannot close the gap, our immediate future depends on successfully integrating this system of biology, physics, and geology to actively manage the atmosphere.